This lesson we're going to look at extrema. So these are the biggest and smallest values. So starting out here, extrema are the largest or smallest values on a function. So it's an extrema if it's either the biggest or the smallest, either the largest or the smallest value. And this is on a specific range. It could be the range of the entire function. It could be a limited range of a small function. As you might have guessed or be exposed to from before, maximum is the largest value, and minimum is the smallest value. Again, this can be over the entire function or over a specific range. If we're talking about, let me just make sure I have these right. Yeah, just make sure I have my order right in your notes. If we have a local extrema, that means it's the largest or smallest compared among the neighboring points. There's a technical definition for what, a better technical one, but this is more understandable. It means just if you look at the points right nearby, this is the largest or the smallest among all of those. Then you also have two names for this. One is the global. The other name is the absolute. So if you have a global or absolute extrema, you are comparing it to the entire range. Again, that might be the whole function. That might be a predetermined, just this chunk of the function. But the global or absolute extrema are the largest values or the smallest values along the entire range. Okay, let's talk briefly about the number of extrema on a given range. Again, that can be specified to be finite or infinite. A function may have it may have both an absolute max and an absolute minimum. So it could have an absolute maximum and an absolute minimum. It could have only one of those, so only an absolute maximum, only an absolute minimum, or it could have neither. So this is just talking about global or absolute extrema. You can have both, only one, or neither. It depends on the specific function. All three cases can exist. Having both, there are cases where there's only one, and there are cases where there are none. There will never be a case where you have, you either have an absolute max, an absolute minimum. Yeah. So the location of that absolute maximum or absolute minimum, how do you find those? Well, they must occur at either the critical points or the endpoints of the interval. So this is going to be a finite number of locations on your function, right? Because you're going to have, you can easily calculate all the critical points. Well, it'll generally be finite. You can calculate the critical points. You can also look at the endpoints and compare all of those. If the endpoint of an open interval, though, would be an absolute extrema, that extrema doesn't exist for the interval. So for example, if I have, I'm just going to sketch it for you, a function that looks like this, and these are my endpoints of my interval. Because this endpoint is open, I don't actually go to whatever this value is in my function. I can never get to the largest value. It does have an absolute minimum right here, because this endpoint, it's a closed interval. I can get to the exact endpoint, say this is 2 and this is 4. Here, I can plug in 2, I can get the smallest value. Here, I'm not allowed to plug in 4 because 4 is a discontinuity there, a removable discontinuity. But I can always pick bigger numbers that are slightly closer to 4, and therefore there's no single value that's the absolute extreme. The same thing is going to be happening if you go off to infinity. If the function goes off to infinity, then, and that would be the maximum, even if it's got an asymptote, it doesn't have an extrema because we can't actually plug in infinity at the end. Okay, extreme value theorem. If a function is continuous over a closed, what did I say? It's not closed. Let me check my notes real quick. Oh, it is closed, yeah. If a function is continuous on a closed bounded interval, it must have both an absolute maximum and an absolute minimum. So I had said before that you could have cases where there are both a maximum and minimum, cases where there's only one of those two, and cases where there are none. The extreme value theorem says in these conditions, when it's continuous, when it's a closed interval, when it's a bounded interval, both of these have to be there. So on the previous slide, I'd given you the example with the open. Now if I close both ends, we can see there is a biggest and a smallest value here. Even if it's a straight line, and imagine that's flat, all of these values are the absolute maxima and the absolute minima because they're all the same. To be an absolute maximum or minimum, you just have to be bigger than or equal to every other point on the interval. So if the interval is closed and it's bounded, that means there's a finite range, then one of those points has to be the largest, one of those points has to be the smallest. So that is our extreme value theorem. This topic will make more sense as you get into more practice with it, like the nuances of it, but hopefully at least intuitively, kind of the basics track so far. Let me know if you have any questions.